Hey guys, so I want to talk a little bit about what we talked about in class today, which means that I'm going to go back through the idea of series expansion having negative terms, the idea of a pole, essential singularities, removable singularities, their characterization in terms of limits, and then I'm going to also include in this lecture what I'm going to be talking about next time, which is an indication of what the residue of a function is at a pole, and different strategies that we might use to build series around different centers. And in the next section, we'll talk about formally Laurent series, when those things exist, and how we can derive them from a more global perspective. So we're going to begin with talking about the examples that we talked about today. So if we think about the functions f of z is equal to sine z over z, and g of z is equal to e to the z over z squared, and h of z is equal to e to the 1 over z, then each of these functions has what's called an isolated singularity. So all of these have an isolated singularity at z is equal to 0. What that means is that these functions are analytic everywhere in a neighborhood of their singular points, but not defined or not analytic at the singular point itself. So we characterize this with something called a deleted neighborhood. So a deleted neighborhood of a point z is equal to a is the set of all points strictly bigger than 0 in modulus and smaller than some radius r for some r. Tiberius. And so you should think here you've got this open disk, and then you punch a hole out of the center. And so everything around here, the center of this thing has been punched out as z is equal to a. The disk without that center is called a deleted neighborhood of a. And one way of characterizing when a function has an isolated singularity is to say f has an isolated singularity at z is equal to a if f is analytic on some neighborhood, some deleted neighborhood. Of z is equal to a. So all of these functions that we've written out for our examples here, f, g, and h, all have an isolated singularity at z is equal to 0 because that's the only bad point in their domain. They have no other points where they're not defined. Okay, so what we want to do next is we want to try to think about the differences in the behavior of these functions at their isolated singularities. And it turns out to be the case that there's 3 different things that can happen at an isolated singularity, which is exhibited by the 3 functions that we've drawn. The first thing that could happen is we could have a function like f of z is equal to the sine of z over z. And as long as z is not equal to 0, this is an analytic function. And in fact, we can expand the sine of z as a power series. It's going to be convergent. And certainly multiplying a convergent power series by 1 over z is still convergent. So what we get here, if we expand it, is f of z is 1 over z times the power series for sine, z minus z cubed over 3 factorial, plus z to the 5th over 5 factorial, and so on. Just like in the case when we have a removable singularity for a function of algebra, because I can factor a z out of the power series and it cancels with the z in the denominator, it's like it wasn't really an asymptote for the function. It was just a deleted spot in the domain. So I can think of this as z times 1 minus z squared over 3 factorial plus z to the 4th over 5 factorial, and so on, divided by z. And the algebra says then that this series is 1 minus z squared over 3 factorial plus z to the 4th over 5 factorial, and so on. This thing is analytic. And the limit, even though we started with the assumption that z was not, this is not defined for z equals 0, if we take the limit as z goes to 0 of this thing, well, it certainly isn't hard to believe that all the z's go to 0, and so this whole thing is equal to 1. So this actually has a limit as we approach this singular point. And that means we can fix this function by sort of plugging in the gap. So if we define a new function, f hat of z, to be equal to the sine of z over z when z is not 0, and 1 when z is 0, this thing is analytic everywhere. And that kind of singularity where we get this algebraic cancellation and the function actually has a limit as we approach its singular point, that's called a removable singularity. And in fact, we just did the removing process where we redefined the value of the function at that point to sort of smooth it out and fill in the hole. So this is one kind of possible behavior, which is a removable singularity. Okay, so the next kind is exhibited by our next function. So if we look at g of z is equal to e to the z divided by z squared. And we run through the process that we did before, so assume that z isn't 0, so the function is defined. Expand e to the z as a power series. Then g of z is going to be equal to 1 plus z squared over 2 factorial plus z to the 3rd over 3 factorial, and so on, divided by z squared. And if we go term by term, which we're allowed to do because we have an absolutely convergent, uniformly convergent power series everywhere in C, this turns out to be equal to z to the minus 2 plus z to the minus 1 plus 1/2 plus 1/6 of a z plus 1/24 of a z squared, and so on. So this is a function that has a convergent series. But this convergent series is a Taylor series plus some stuff that has negative exponents. So these dudes right here, these guys, these have negative exponents. In some sense, what those terms do is they capture the fact that this function has this z squared in the denominator. And in fact, the presence of these terms is going to be accounted for in the definition here. So you notice that the highest negative power in this series is -2. So we actually call this kind of singularity where we have this behavior where there are like a finite number of negative terms in a series expansion for the function. We call this a pole. And this particular pole is a pole of order 2. And we're going to make this more concrete, but it has to do with the fact that there is a z squared in the denominator. With a little bit of terminology here, this part of this expansion is usually called the analytic part because it's analytic everywhere, and this part is called the singular part because it encodes the behavior of the function at the singularity. Another thing to notice here is that if you took this function and you multiplied it by z squared, so if you took z squared and you multiplied it by z to the -2 plus z to the -1 plus 1/6 of a z, one was the 1/2 there, plus 1/2 plus 1/6 of a z, and so on, that now this thing would actually have a limit of 0 as z goes to 0. So this is now equal to 1 plus z plus 1/2 of a z squared, and so on. So this limit exists as z goes to 0, but if you multiplied it by a power of z that's 1 higher, so if you multiplied the same series but now by z cubed, z to the minus 2 plus z to the minus 1 plus 1/2, and so on, you end up with a series 1/2 z to the third, and so on. This limit as z goes to 0 is 0. And the fact that the z squared had a limit that wasn't 0 and the z cubed has a limit that is 0 is how we're going to end up characterizing exactly what we mean by a pole of order 2. The third type of singularity we have to deal with is called an essential singularity. These are harder to untangle and harder to understand. So an essential singularity we can look at this function h of z is equal to e to the 1 over z. So as before, assume that z is not equal to 0. And this time what we're going to do is use composition to feed the 1 over z into the exponential function. So if we do that expansion, we're going to get 1 plus 1 over z plus 1 over z over 2 factorial, the squared there, 1 over z cubed over 3 factorial, and so on, which normally we write 1 z to the minus 1, 1/2 of a z to the minus 2, 1/6 of a z to the minus 3, and so on. And the the negative powers of z never stop. So there's infinite negative powers of z. And when we have infinite negative powers of z, we can't call it a pole of order k because there's no order k. Any z to the k I multiply this thing through can't possibly kill all the negative powers. This is exactly what we mean when we say that a function has an essential singularity. Okay. So isolated singularities come in 3 flavors. If f of z has an isolated singularity, and z is equal to a, one of 3 cases holds. 1, a is a removable singularity. And the condition for this, the definition for this, is that the limit as z goes to a of z f of z is equal to 0. This is called the Riemann condition. Sorry, this is not z. Z minus a f of z. Essentially what you're saying is that you're multiplying the z minus a out of the denominator. So if this limit is equal to 0, then the singularity was removable. Okay, so we can actually see that if we compute the limit as z goes to a, z goes to 0 of the sine of z over z times z, then we get the limit as z goes to 0 of the sine of z, which is 0. And so this must be removable. Singularity for f of z is equal to the sine of z over z. Now this isn't always so obvious what's going on here. Another possibility that you might like to look at where there's not an immediate simplification like this, we could look at something like the limit. This is example 1, really easy because the z cancels the sine of z over z. We could look at the limit as z goes to 0 of something like z times the sine of z over the tangent of z. And now things are a little bit more complicated because if we set this up in the following way, z sine z over tangent z, it's not immediately obvious what order, you know, sine z, or sorry, tangent z obviously is equal to 0 at 0. So there's something going on there. The 0 is a singular point. Z equals 0 is a singular point. So one observation that you can make here is that you can replace z sine z with its power series and tangent z with its power series. That'll look like the following. So we're going to get z times z minus z to the third over 6 and so on, divided by, okay, so the power series for tangent is z plus z to the third over 3 plus 2z to the fifth over 15 and so on. And if you rewrite that with some simplification, the limit as z goes to 0 of z squared minus z to the fourth over 6th and so on, divided by z plus z to the third over 3 and so on. You can use the same trick that you use sort of in pre-calculus, where you divide everything by the highest power of z that you see, in this case z squared. So let's multiply top and bottom of this by 1 over z squared, and that limit will still be equal to the limit as z goes to 0 of 1 minus z squared over 6, and so on, over 1 over z plus z over 3, and so on. And if you compute that limit, well, as z goes to 0, the top goes to 1. The bottom is going to infinity because we have this 1 over z term. And so things that tend to 1 over infinity tend to 0. So this limit is 0. So that means that sine z over tangent z actually has a removable singularity at z is equal to 0. So sine z over tan z has a removable singularity at z is equal to 0. All right, so let's look at another condition. So the second possibility, so remember that what we had here was that the first behavior that could happen is that A is a removable singularity for the function. The second possibility is that A is a pole of order k. A is a pole of order k. And the way that we check for A being a pole of order k is we compute the limit computation that we saw before. So in the limit computation, so this happens precisely when the limit as z goes to a of z minus a to the k plus 1 f of z is equal to 0, but the limit as z goes to a of z minus a to the k of f of z is not equal to 0. And what this condition is picking up is the existence of these potentially z to the minus k terms in a power series expansion for this. So an easy example would be something like f of z is equal to 1 over z plus 1 squared times z minus 2. So this has a pole of order 2 at z plus 1 at z equals 1. It should be obvious that what's counting here with poles is that we're imagining that for rational functions we're just picking up the power of these terms in the denominator. And if we look at the limit as z goes to minus 1 of z plus 1 squared times f of z, then we get the limit as z goes to minus 1. So it's supposed to be minus 1, not plus 1. Okay. Of z plus 1 squared times 1 over z plus 1 squared z minus 2, which gets you the limit as z goes to minus 1 of 1 over z minus 2, which is minus 1/3. And by itself, that's not enough to check that we have a pole of that order. So we should check to see that the next power of z gives us a 0. So, and the limit as z goes to minus 1 of z plus 1 to the third f of z is equal to the limit as z goes to minus 1 of z plus 1 over z minus 2, which is equal to 0. So we got a non-zero limit for k is equal to 2. We got a 0 limit for k is equal to 3. The condition says that that means that this is a pole of order 2. So f of z has a pole of order 2 at z is equal to minus 1. The third possibility is that A is an essential singularity. A is an essential singularity if A is an isolated singularity and A is not removable and not a pole of any order, then A is essential. And another way to look at that is that's the same thing as saying that the limit as z goes to a of z minus a f to the k, f of z is not equal to 0 for any k. And that corresponds to the infinite negative powers in the series expansion. So the natural sort of functions that we want to think about when we're thinking about singular functions are a class of functions called meromorphic functions. So here's the definition. A function f is called meromorphic if f of z is equal to a of z over b of z, where a of z and b of z are analytic functions, and b of z is not identically 0, because dividing by 0 identically would not be a very interesting function. So meromorphic functions correspond to the behavior that we see in the first two cases. So when we look at the function f of z, which is equal to sine z over z, this is meromorphic because a is equal to the sine of z, and b is equal to z. G of z was e to the z over z squared. In this case, the function a was equal to e to the z, which is analytic everywhere. B is equal to z squared, which is an analytic function. And finally, h of z, which is equal to e to the 1 over z, this is not meromorphic. And what we're going to find is that these cases, which are the meromorphic functions, carry the behavior of poles and removable singularities inside of them. And essentially, the long-term goal here is one of the things we're going to show, so long-term, is any meromorphic function is going to turn out to be approximated by rational functions. Which is kind of a useful thing. So that's kind of the long-term objective, is to say that that's true. So normally when we compute the power series of either a meromorphic function or a function with an essential singularity, The easiest way to do it is the sort of computations that we've already done. So we wrote down that the sine of z over z turned out to be equal to 1 plus minus z squared over 3 factorial plus z to the 4th over 5 factorial, and so on. And e to the z over z squared was equal to 1 over z squared plus 1 over z plus 1/2 plus 1/6 of a z plus 1/24 of a z squared. And e to the 1 over z was equal to 1 plus 1 over z plus 1 over 2z squared plus 1 over 3 factorial, 6z to the 3rd, and so on. So now imagine that we're looking at a punctured disk, punctured out at z is equal to 0, and we try to set up some kind of integration of these functions around a contour contained inside of here. Without getting into the details of how you would draw the contour, you can't use the Cauchy integral theorem because this thing is not even defined at z is equal to 0, so the Cauchy integral theorem isn't going to work. So probably we're going to have to use some trick where we disconnect the region and go around this singular point. If you integrated these terms, one of the things we've seen over and over again is that the integral of 1 over z is that the integral of z to the n dz around some closed contour is equal to 0 if n is not equal to -1, and it's equal to 2 pi I if n is equal to 1. And so that n equals, -1. And so that n equals -1 term is really special. And it's so special that we give the coefficient of that term a name. So this term right here and this term right here, the coefficient that is attached to that z to the -1 term, because it's the term that survives these sort of integrals, right? The integral, that number is important enough that we give that coefficient a special name. So it's the coefficient of the z to the -1 term. So the residue of f is equal to the coefficient of the z to the -1 term. So the residue of e to the z over z squared calculated at z is equal to 0. So that tells you where the series center is. This says the series center. This tells you the function. That residue is equal to 1, because this is 1 times 1 over z. Likewise, the residue here is 1. So the residue of e to the 1 over z for the series centered at 0 is also 1. Here, for the first term, the residue of the sine of z over z for the series centered at 0 is 0, because there is no z to the -1 term. So the idea is that when we have this sort of expansion and we have a z to the -1 term, the coefficient that carries is called the residue. And it's going to turn out to be the case that there's this theorem that says that the integral of a function around a singular point that's isolated is equal to the residue of the function times 2 pi I. It's called the residue theorem. We don't have that yet. You can look at a preview if you want. So this is a preview. This is eventually what we're going to show is that if we have a contour that has a single isolated singularity on the inside of it, so you've got some C, it surrounds one singularity at z is equal to z naught, it's going to turn out to be the case that the integral around C of f of z dz is going to be 2 pi I times the residue of f taken at z naught. So that's sort of gives us a theory of integration where if we can decompose contours and we can come up with these sort of series that we've seen before, we have a very nice theory of integration we can use to connect up the series behavior with the behavior of these contour integrals. So this is sort of our goal, is to build a theory that lets us develop that theorem and then use it to calculate various integrals. So our first order of business here in the next section and where we're heading with this is we really want to make the idea of these series with negative terms formal. So we want to formalize the idea of series with negative terms. We want to know something about where they converge. We want to know something about the way that functions behave on the sets where these things converge. We'd like to know how to write them down, how to compute their coefficients. So when do they exist? When do they converge? How do I compute the coefficients? I mean, it's going to be hard to use the Cauchy integral theorem to compute the coefficients like we did for Taylor series because these functions aren't defined at the places that we're trying to center these sets, at the isolated points in the middle of the deleted disks. So all of these things are going to be talked about when we discuss the notion of Laurent series. Okay, so I hope you found this enlightening. What we'll talk about in class next time is we'll do some more work with expansion of functions around different singularities using Taylor series ideas naively. And then we'll start building our way towards showing that Laurent series exist, that you can compute the coefficients for them, and that where they exist, they're unique. Okay, so I'll see you next time.